Okay, so today we are doing problem 6.8 for redundant connection. Is problem 3 is an undirected graph that is connected as no cycle. So we given some graph that started as a tree and added one edge. Edge between different vertices and one that doesn't exist. Whatever. So the result, if there are multiple, return the answer that occurs last in the input. Okay, so how big is the input? 1000. There are no repeated edges. The given graph is connected. Okay, well, what that edge does, I think, is it creates a cycle, right? Exactly one cycle. Now what do we want to do? Let's say we just start the FS from somewhere, right? Eventually, we visited this node, right, already. And it's not the parent. So then you want, okay, so let's go back towards the stack, right? And then we have this edge, this edge, this edge, this edge. And we pick the edge with maximum number. And if we store the adjacency list like this, right? So instead of storing that in adjacency of 1 is 2, we store in adjacency of 1 there is a tuple of 2 and 1, meaning that is the first. Then we can do this in linear time. So not sure how I get n, to be honest. That quite sucks. So AB is, what the hell? So both A and B are less than or equal to the length. So n is, oh my days. Okay, so I'm back in Chrome because Firefox crashed. So n is len edges, right? And then okay, so I want to build the adjacency list for x I x enumerate edges, and then adjacency x append yi adjacency y append xy. Great. And now that we have done that, let's do def dfs vertex parent and stack, and then we also need like this right, and then for ui in hv, and now if this u and u don't equal parent, if not this u, dfs uv stack, not sure I want it, so I want to do like stack append ui, and otherwise if this happens, then we want to, so first we got this edge, right? So ans is 0, right? And then or -1, or maybe I can technically do non-local ans, right? And then ans ans, max ans. No, we do ans is equal to I, and a while stack -1 don't equal u, right? Then we want to do index, or like h index is equal to stack pop ans max ans h index return, and I think this should work, but I'm not sure. Okay. V is not defined, so I guess from 0, list index out of range. That's weird. UI stack. Let's see. VUIP, so that's first index. So basically we started at what? So we first started it here, then we went here, then we went here, right? So that's, we were here, U is here, also problem is with this. I mean, maybe this will work. No. How is this possible? I mean 1, 3, 4. So 1, 3, 4, 5, 3, 2, 3. So 1, 2, 3, 5, 4. Okay, and then I start at 0. That's weird. How is this possible, man? So something's up. Zero, 3, 4. So done. Edge size. Okay, and then what? Void int int parent. I mean stack is probably just wrapper on whatever, but like this. Oh, right, and then this v1. No, I want to push into stack here. No, I don't. Okay, it's nice. Const auto UI in HV, if not vsume dfsuv stop push UI stop pop if with u and you don't equal p ans I. While not the empty and the back first don't equal u, then ans max ans the back step up. Maybe, I don't know. That's interesting. CPP debugging session. Let's keep those cases. So what are we doing? Which case? It's case 2. So I go like this and then Runtime error. What even is this, bro? What a pointless video, bruv. So immediately we go 0, this. Okay. So was that the entire Python error? If ans is not -1, return. Yeah, looks like it. Fair enough, I guess. It's 21. Yeah, that didn't change much, but suddenly time is 0 milliseconds, beat 100%. Nice. Let's write a solution which nobody reads and I can't even submit it, so H creates exactly one cycle which we can detect with a DFS, and if we keep the node in the DFS on a stack, we can pop the vertices from the stack until find the current one. We find by checking if a neighbor is visited and it's not the parent. Last edge in the input, we store the graph as a adjacency list with pairs node index edge index for each neighbor for each node, and then if we keep the path from start from we can pop we simply pop the edges of the stack until we get to the current node, storing the maximum indexing while popping plus current edge index. Of the vertices, since we just do a DFS and takes O n plus m, where m is the number of edges, which in this case is n, and then we once pop some vertices from some at most space complexity on, since we use the adjacency list to store the graph, and at most n vertices are on the stack, and the recursion depth is at most n, and on each depth we store 2